is, and then I'm going to share on why do we need software in the controls design, why is it so important. Next, I will talk about the control systems design workflow and how you can model the plant in a control system in Simulink, and also the control system process in Simulink. Okay, so what is Simulink? Okay, I believe all of you, when you were younger, you played with this thing. Sorry, can you all share my? Can you all see my screen? Sorry, can you all see my screen? Anyone?
Yes, I can see your screen.
You can see my screen, right? Okay.
Yes.
Okay. All right. So I believe when you all were young, you all used to play with this game. It's Lego. So in Lego, what they provide are standard blocks. Example like this one in blue, you have 4 studded, and the one in orange, they have 3 studded. And how many systems can we build with Lego? We can build infinite amount of systems, all depending on your own creativity. So similarly with Simulink, Simulink is an environment that we call as a block-based programming. So in Simulink, we also provide you with many blocks from very fundamental blocks like mathematical operations up to application-specific blocks. Example, like if you are focusing on aerospace or communications or neural network, etc. So depending on your own creativity, and for those of you who have used Simulink before, you know you can build many types of systems. Okay, and of course Simulink doesn't end here. It's not only in simulation environment. Why the commercial people use Simulink is because one main thing is for the code generation, but we won't be touching code generation today. Okay, so why do we need control systems? Okay, if you all have kids, you know that if you leave your kids alone around the house or at the park, they will do whatever that they want to do. They will jump around, they will climb up the tree, they will jump into the lake, etc. And as a parent, we will tell them, hey, do not do that, so that you won't injure yourself or so that you won't get dirty. So similar to this analogy, why we need a control system is we want the plants, which is our kid in this analogy, to follow what we want them to do. So similarly, if you have a a machine, right, without a control systems, it will just, example, let's say a robotic arm, right? If you just let it run, it will go and do things by itself. Okay, and one of our main reason of building control systems is we want it to follow what we want it to do. Okay, so that's why we need a control system. And why do we need to design? Why it's recommended to design your controls parameters, tune your controls before you even go to the real thing. As you all know that this, okay, example like in this robot here, it is a big robot. Okay, it's a KUKA, and it could even be be bigger. And if no robotics manager or a plant manager will let a newbie and then just dive into their plant and just set anything into their set anything into their plant, because this robot will just go haywire. Okay, so one reason, first reason is for safety. So we do not want any injuries to happen. And the second thing is cost. You all know that this kind of robot here, it will cost around hundreds of thousands to a million ringgit. Okay, and even for education side or a smaller commercial entity, the robots or the plants will cost at least minimum a 1,000 ringgit. So it is better to make sure that all your design is tuned properly in the software environment, so that you won't damage the robot lah. Okay, and lastly is time. If you all design a control before manually, okay, I have my own experience also designing manually. Mine is more on designing a moving platform, and it takes a long time. Okay, I believe all of you who have done controls before, if you do it manually, it will take some time because it really requires knowledge lah. And not only that, and even sometimes you manage to make your robot to move to, example, to do what you want to do. Example, let's say this robot to move to a point here, right? But we won't know if this robot is taking the shortest path or the most optimized path, or the least amount of energy. So we would want to do optimization in the human environment, in the software environment first. Okay, so this is the control systems workflow. I believe all of you have done controls before. This workflow will be very familiar to you all. So what we have is the plant, okay, and then before the plant we have the controller, and also the input, output, and the feedback loop. Okay, and when we design before we start the control system design workflow, the first thing that we want to do is to design the plant. Okay, the plant can mean anything that you can imagine. Your motor, your even your power plant, or your aircraft engine, or even a hair dryer, your robot, etc. Okay, and after your first step, then you design the controller and build your feedback loop, and so on. Okay, so there are various ways of doing plant modeling. Okay, plant modeling, there are three ways to it. So example, okay, so there are three ways to it. So one is the first is if you you know everything. Okay, second is you know something. Oops, sorry. Okay, first is oops. Sorry. Okay, first is you know everything. The second is you know. Oops. Okay, sorry, something's wrong. Okay. Anyway, the first is you know everything about your plant. The second is you know something about your plant, and the third is you know nothing about your plant. Okay. So this will let you know which way that you want to go. So if you know everything about your plant, you can use first principles. So what basically first principles is, if you know everything about your plant. Example, the equations that build up your plant. Okay, and then you can model it in the Simulink environment. Okay, this is what we call as physics. If you know the physics of your plant, and then you want to model it in this way. But these are usually more for very deep research, usually for those who are doing PhDs or yeah, very deep research. And the other way of first principles modeling, if you do not want to use equations, you can use also component-based modeling. So what component-based modeling is that instead of using equations, right, you use components. Okay, use components. So example in here, just now we model it in terms of equations. Now we just connect your damper, your resistor, your mass, etc., and connect it into the line. So this is supported by in Simulink as by what we call as a physical modeling product. Okay. The second approach is what we call as a data-driven modeling. So data-driven modeling, which means we know nothing about the system, and in this way, what we do is that we have the input of the system. Okay, we have the input of the system. It goes into the real machine. Okay, and then you collect the output. Okay, then based on this output and input, you can create a transfer function using system identification. Okay, you can also use statistical methods using model-based calibration or neural networks. Because neural networks is very famous today. Okay, so this is data-driven modeling, and the third way, the last way, is a combination of both first principles and data-driven modeling. This is if you know something. This is if you know something about the system. So, example, you know the equations. You know the equations of the system, but then you do not know the parameters. Okay. These are normal. Sometimes the parameters is easy for us to get. Example, let's say if you're modeling a part of the system, let's say a motor, it's easy for you to get it from the spec. What is the what's the coefficient, what's the friction, etc. But there are some parameters like in the real world, there are friction, there are viscous forces, there are yeah, other type of more difficult parameters to tune. Then we use parameter tuning to tune our plant. Okay. So here's just a summary of what are the relevant toolboxes to cater for all these things. So example, in the first principles, you can use Simulink, Simscape, Simulink Math, and Simscape product. And in data-driven side, you can use system identification, neural network, and on the parameter tuning side, you can use Simulink design optimization. Okay, so I'm going to go. This webinar is focusing on controls design in Simulink, and of course you know that MATLAB has 90+ products in our family of products, and controls design is actually controls toolbox is our first toolbox. Is the most mature toolbox. If you go to the MATLAB and type version, right, you'll see that controls is a very mature toolbox. So it's used almost in every universities and companies to design your controls. Okay, so the first thing you do in the control design is you want to model your plant. Okay, and after you model your plant and of course the structure of your system, okay, the plant, the control, the feedback loop, etc. So then you pick the blocks that you want to tune. After tuning it, yeah, this will be a bonus demo that I'm going to show you today. This is what we call as a response optimization. This is the most powerful thing that you can have in a controls design. I will show this demo later on, and then after you tune it, you just write it back. You just update the parameters in Simulink. Okay, so I'm going to show you 3 demos after this. So the first demo will be the fastest and most straightforward way for you to design a controller. So okay, before I go there, let me show you the Simulink library. Okay, so this is how the Simulink library looks like. For I know some of you are familiar, and then we have many blocks. You can see there are all these blocks for you to build. Okay, and then to build a model, what you need to do is just click new, right, and then you just drag the block inside here, and then you start to just drag the block inside here, and then you start to connect. Okay, so I'm going to show you the first demo using the displan data. Okay, so this is a model of a displan using equations. Okay, in this demo, in this webinar, we won't be touching on how we are going to model the plant. If there are a lot of you who are interested how you can model using various approaches, you can let us know. Then we can create another webinar just to cater for plant modeling, because plant modeling is another big topic. Okay, so I'm going to run this model, and you can see that currently this is what the end effector of this head assembly is moving. It is going like this. So this is something that is that's undesirable. We do not want it. We do not want it to move this way. Okay. So what I'm going to do is I'm going to create a step response. Okay. At time 1. And goes to a value because it is this head assembly. I know that the distance is very small, so I'm going to put just a very small 2e minus 4 current into it, and then I'm just going to put this there. Okay, so I'm going to add okay, I'm just going to create a structure of a controller, and if you all know it, and then a feedback loop. Okay, so I'm going to run again and see how it moves now. So what you can see is currently the model is moving this way. This is the step response I give, right? And it goes up like this, and then over here it becomes like this when there's a disturbance, there's a torque disturbance. Okay, at time equals to 10. Okay. Okay, so the fastest way to tune for those who are new and you want to get a quick result, right? Of course, this tuning capability on some standard specifications within MATLAB. Okay, you are not able to change it. So when I double click into this block, into the PID block, you can see that there is the the PID parameters set for you. Inside this block, you can inside this block are the equations. So I'm going to open the window. You can see this is how it looks like, a PID equation. And if you update this from P to PI, Okay, and then you click apply. You can see the blocks will automatically change for you. Now it's a PI controller, and then or you can change it to ideal. Okay, click apply, and then now it becomes an ideal controller. Okay, so depending on you how you want to do it, then you can click apply. Okay, so what you can do with this block is you can see there's a tune button over here. So just before I click tune, if you want to use this button over here, you need to have Simulink control design toolbox. Okay, this capability only comes with Simulink control design toolbox. If you don't have this toolbox, right, your block here will be grayed out. Okay, so I'm going to tune this model. Okay, and when I click tune, you'll see that this window comes out. This is a PID tuner window, and automatically it will tune for you already. Okay, and will give you some values. Okay, so up to you. You want to change the transient behavior or the response time. Okay, you can play with it. Okay, you can see this is just a basic window for beginners for you to play with. Okay, if you're happy with your model, you just click on this button here, update block, and you automatically update your PID block here, and all your values have been updated just like this. Okay, so maybe some of you might not be able to appreciate it, but if you do a manual tuning by yourself, right, it is really difficult for you to come up with an immediate answer. You know that this will be a good solution. Okay, unless you are very experienced in controls. Okay, so
good question. This is from Mimas. Can you go back to the tuning? So yeah, on the values that are obtained. So the decimal numbers, basically it is based on the PC lah. It's not fixed point, right?
Yeah, it's not fixed point yet. If you want to change to fixed, if you want to change to fixed point, there's another toolbox called the fixed point designer.
Okay, source internal. What does that mean?
Where is it? Sorry.
The pull down under source above the proportional above the P. Source is internal.
P.
Internal means what?
Okay. Honestly, I haven't explored this site yet.
Okay. But basically, this tune thing is new.
No, this has been there for a very long time.
Okay, but you need to get the toolbox, right, to be able to access it.
Yep, correct. Yeah.
Okay, and basically you can change the frequency response and transient response, and then automatically adjust lah. Basically, this is the response.
Automatically adjust. Yep.
This is the step response of the PID, right? Not the full system, right?
Of the full system from here from.
The full system from the step response equals to the output of theta, is it?
Yes. If I run this model again, right, you'll see that
together with the top system.
You see that now the system responds better lah.
Okay, where's the top disturbance coming in? That blip there, is it?
Okay, wait yes, right. The top disturbance part is here.
Yes,
okay. Small notch there. Yeah.
Okay, so
sorry, I didn't plot this together. Let me. If I run it again.
So basically, by putting the PID in the control loop, we are adjusting the step response at the initial to be good. So the blue one is the step response, the yellow one is the output theta lah. So it overshoots a little bit, and then the disturbance come in there. It doesn't oscillate like crazy lah.
Yes. Correct. Yes.
Oh, very powerful.
Yeah. So for those of you who play with controls, you will know what I mean. You will appreciate it. Because last time I did manual tuning before, takes you a long time. It's very long. So
what algorithm does it use for the tuning? Do we know?
The algorithm, yeah, it's all inside the documentation. I can send to you via email later.
Okay.
Okay.
Hmm.
Okay. So this one is sorry, I continue, yeah?
Yes, go ahead, yes.
Okay, all right. I will build up to the climax. The climax will be the last demo. Okay, so I'm going to close this. Okay, so now I'm going to show you a manual way of tuning, just to give you all what are the capabilities of Simulink environment. So this is another plant. Okay, just now there was a plant of a disk controller, and now this is the plant of a DC motor. Instead of using PID, now I'm going to use a transfer function, just one-on-one. One-on-one means one, so basically this block doesn't do anything. The signal just goes through like that. Okay, so for manual tuning, you need to specify what is the inputs, what are the outputs. Okay, to specify that, you can just right click here and click on linear analysis points and selecting input perturbation. Okay, so I'm going to run this model, and you can see that currently this model is performing this way, and this is the input graph, and this is the output. So it's not performing to what we want it to perform. So what you can do is you can go to the controls system designer over here. Okay, so when this controls app open, it will automatically ask for you to tell it which is the block that you want which is your controller. So I know that the block is the transfer function. Okay, it will try to automatically detect which is the controller and then give you suggestion. Okay, and then you just click. Okay, that's the block that I want to tune. Okay, you can also add your signals. This one will be automatically detected from what that you set here. Okay, your inputs and your outputs that you want to tune. Okay. So when you are done, right, you can just click OK, and it will generate this. Okay. So now we are going to I'm going to show you how you can do some open loop. This is where you can do your open loop design. So you can just click on your body plot. Okay, select the loop transfer, plot it. Okay, so this is your body plot. You can add the grid. You can see this, and then I'm going to add another left, right, and I'm going to put a root locus. Okay. So in here you can see that these are root locus, and this is where your gain is. You can actually change this gain manually, and everything will change. I'm just going to show you. Let's say we turn on some analysis plot. Okay. First I'm going to custom. Okay, I'm going to turn on a new step response. Okay. So I'm going to add a signal to the list. This is from here. So I'm going to analyze the step response from here to there. So the input is wref and the output is w. So I'm going to input is w and this is wref. Okay, doesn't. Oh, sorry, doesn't look right. 1 second here. The input. Okay, this is input. Okay, input is wref. The output is w. Okay, yeah, this looks more correct. So this is the step response of the model, and then you can. I'm going to add a new body plot also for between the load disturbance and the output. Sorry. Body plot. Sorry. Load disturbance input and the output W. Input output. Okay. Okay. So this looks correct. So so you can see that what we want, right, from this model is we want it to go from this is our current output.
Quick question. What is your disturbance? Is it a step also, or
Oh, good point. Okay.
what is it right now? It's load disturbance 1.
Now is getting this from input. So
Let's see. I don't know.
okay. Oh, now there's nothing.
Oh, okay. So
Now, yeah, sorry.
but previously you put what, a step also lah?
You can put a step. You can put a noise. Maybe it's doing something like that. Yeah, or you can put a.
It can be
yeah,
random noise. It can be
Yep.
a step. It can be some frequency related noise also lah.
Yeah, correct. You can put. Yeah. All right.
Okay. Continue.
Okay. All right. So where were we? Okay. Yeah. So this is our current. Sorry. So this is our current output, and we want it to go. This is our ideal. This is our ideal output. So we want it go from yellow to blue, and one way we know that we can push this up is by increasing the gain. So if you go to this plot, right, and you adjust the gain, right, and take note on this step response. Currently it's at 0.2. We want it to go to 1. So if you drag your gain value, right, okay, and increase the gain, you notice that it will go higher. It will go higher and higher. Okay, and you can actually go into this compensator editor by double clicking into your tune system here. Okay, and then here you can actually have, if you go to parameter tab, you can actually have a slider that you can just increase. So if you see now the current value is 3.241. If I increase it gradually, okay, to 4.132, take note that this step response is increasing.
This, when we are changing all this on the fly, right, is happening real time. It's updating the graphs. What are you changing actually? The DC motor parameter or the transfer function before the DC?
The transfer function, the gain. This
The
one.
gain, which is the 1 by 1, you're changing that 1 by 1 thing.
Yes, correct. So currently, initially it's 1 by 1, right? And now it is 6.805.
So you're changing. Okay, so basically you're adjusting the P in a sense.
Yes, correct.
Okay, got you. Okay, continue.
So, yeah, so I'm adjusting this one. Yeah. So yeah, of course you can do your manual tuning. So let's say you're now I'm push it up to close to 1. So let's say I'm put it around here. I'm happy with it, and I know that if I'm going to, but there's still error. Now it's around 0.7, and the value that we want is 1. And I know that if I add an integrator block, it will just reduce the error. The error will go to 0. So I'm going to add an integrator block, and now you see that now the equation has become this multiplied by 1 on S because of the integrator, right? And now you see that the final value has go to 1, to what we want. Okay. So you can, if you want to add a PI controller, you just need to add another 0. So now it's the PI controller. Okay. So when it becomes PI controller, you see that now it is of this value. Okay. And there are more things to this graph. If you want to, let's say, set some design requirements, let's say you can come here and see your settling time. Okay, so from set response, we see that okay, this controller now the settling time is 3.49 seconds. Okay, but maybe you think that 3.49 seconds is not too fast. Okay, I want it to be faster than that. So you can actually go here and then you can add your design requirements. Okay, I'll put a new design requirement. Setting time. Let's say I want it to be around 1 second. Okay, so you see in this graph here now, right? It's updated with yellow shaded region. I'm not sure you all can see it. But this yellow shaded region is where we don't want the gain to be in. If it is inside here, it will be more than 1 second. So it must be out from this region, in the white region, then it is below 1 second. But of course you can see that now there is one gain here that is stuck, is forever stuck because the pole and 0 is over here. So it's forever stuck in there. So we need to do some manual adjustment to this. Okay, you can also do other design requirements like let's say I do not want it to overshoot by more than 10%, example. Okay. Then this will be your another design requirement. Okay, so you can add a design requirement and then tune based on what you want it to be. Okay, and there's also another button here which you can do more automated tuning. Okay. Sorry, can you all hear me?
Yes,
Hello?
yes, can hear you.
Okay.
Yes, no problem. Yeah, we can see the shaded yellow. No problem. Yes.
Okay. All right. Okay. So this is automated PID tuning. So in here you can set your transfer function and then you can select your tuning methods. Let's say I'm select your PID now. Okay, update compensator, and automatically it will become a PID transfer function. Okay, so this is an automated tuning. It will give you some results. Okay, some results, and you can see whether it fulfills to what you want it to be now. For example, like now it is already in the below 1 second. So is this good for you? Is up to you. Okay, you can also put new design requirements here. example like maybe you want to put, okay, the maximum rise time I want it to be here will be example 0.1 seconds, here 0. Maybe here 0.25 seconds. Okay, so this is the new this is your design requirement lah. Okay, or maybe your boss says that, hey, you come with this, you come with this result to your boss, then your boss say, hey, this one's still very slow lah. Can you put it into this white region over here? Okay, can you design your control so that it's only in this white region? Okay, so you can go on trying lah. So I know that of course this is a demo with answers has already been tuned before, so you can actually use the frequency response. I'm going to increase this right to around 100 bandwidth, and the bandwidth to be around 25. Okay, so this is your your final response lah. Okay, that fulfills your desired output. So again, what I'm showing you in this second demo is there are all these plots. Of course, now I'm just showing you the body plots and the road locus plot. There are many other tuning methods if you want to use Nicole's editor, etc. Okay, it's all all your choice. Okay, so this is the manual tuning method. After you tune this, if you're happy with this, you want to update your block, you just click on update. Okay, now I've updated my block, and I go back to the Simulink model. Right now, you see just now the block initially it was 1-on-1, but now it is updated with your latest parameters.
Quick question. So right now this is for motor related control loop, right?
Yep.
Is it possible to have it for like op amps, for electronics?
Yep. Yes.
So
and
what is that? Is that a special toolbox or?
Your control is analog control or
Let's
this way?
say it's yeah, analog control with the op amp.
Oh, I see. Yeah. If you want to do analog control, there is another
Toolbox?
library.
I mean, this is right now
toolbox, yes.
control. It's a control toolbox right now you're looking at, right?
Yeah. For this demo, yes, it's from the control toolbox.
Control toolbox, okay.
Yeah. But for the one that I think the one that you are doing is analog control, right? So it will be a lot of op amps and
electronics,
things.
Right? Isn't it? Yeah. Yeah,
electronics. So for that, you can use this library lah.
Oh.
Yeah. The one.
Oh, so you're basically building the circuit here. Oh.
Yeah, not on this demo, but you can
by using the elements in your thing lah.
Yep, correct. This one is actually what we call as physical modeling lah, the one I talked about in the slide just now. But yeah, this one is under plant modeling. I can, if there are a lot of you who wants to see plant modeling, I can touch on this topic the next webinar.
Okay. So basically, all of these are basically ideal related elements with parameters where you can define the non-ideal stuff lah, right?
Yep, correct.
For example, op amp, you probably can define open loop gain, input resistance, output resistance, step response, those kind of things lah.
Yep, correct. Yep.
Okay. Interesting.
Okay, continue. So now I have updated the new the one that I've tuned into this Simulink model, and you see that after I run this model, the output will be at least closer to what I wish it to be lah. If you remember that just now the output was going down like that. Okay. So this is closer to what we want it to be. Okay. So now is the last demo, the third demo. Okay. This is the most powerful thing in Simulink. Just give me another 10 minutes. Okay. This one I will recommend you all to. Okay. Okay. So again, what we have done earlier, right? So far in the first two demos is that one is we just double click into here and tune. This is a very standard beginner's way to do it. Of course, if you want a quick solution, you can get it, but there are limitations. If you want to do further, deeper analysis, you're not possible. And then
can you double click on the DC motor?
Oh, okay. Yeah. So
this is the DC motor.
Yes. Yeah. For this demo, we are just using equations, and definitely we have another demo that we use all this in electronics.
Yeah. So when you go back to the DC motor, so basically you're using. I saw the equation like K.
Yeah.
Okay. So yeah. Those are like motor constants. Okay.
Yeah.
Okay. But you do have like more realistic models of motors.
Yes, correct. We have more. It is
actuator and drive probably. No.
Yeah, I mean the drive. Yeah, rotation actuators. Yeah, we have fundamental DC motor, and then we have more detailed ones lah.
Okay, got you. Okay.
Okay, all right. Okay. So, where was I? Okay. So far what we have done is we have tuned this to achieve this. The first demo we tuned it to achieve. Second demo we also tuned this manually to achieve your output. Okay. And now I'm going to show you the magic is you don't need to tune this. We are going to use this to tune this. Okay, this one is using optimization technique lah. This is actually using the toolbox called as Simulink Design Optimization Toolbox. Okay, so Simulink Design Optimization Toolbox allows you to do response optimization for your controller, or also parameter estimation for your plant. Okay, so if you remember in my slides just now, I talked about well, if you know something about your plant, and then if you want to tune the parameters of your plant, because there are some parameters like viscous forces or friction that is very hard to get the values, you can use the same toolbox. Okay, use the same toolbox to help you design that. Okay, so again, remember to set your inputs and outputs. Okay, so we now are going to response optimization. Okay, so okay, what I'm going to do is I'm going to create a new step response envelope, which means I'm going to create an envelope that tells this model, right, what the output is, and I want to limit it within that region. So I'm going to create a step as response envelope. Okay, so I'm going to say like time is here 1. Set around 0.25, maybe 0.5. Yeah. Okay. Oh, sorry, I need to select the signal. Okay, so I need to select the signal that that I want to monitor, which is the DC motor output, which is this signal here. Okay, so okay. Okay, so now we have set the response model. Of course, you can manually change it by yourself. Okay, you want to change it by yourself is up to you. Okay, and then I'm going to quickly plot the response model. So you can see that currently our system behaves like this. It goes from here when it hits one, when there's a step response, it will go like this. It will go like that. Okay, but what we want is we want it to go into this region. Okay, into this white region, if you see. Okay, and previously we used manual tuning, right? So now I'm going to show you the magic. Okay, the magic of Simulink response optimization. You can, okay, first you need to select what you want to tune. Okay, so I know that in this, of course there are many parameters, and sometimes our model can go up to hundreds of parameters. In this model, I want to tune just, I know I want to tune just this KP, KI, KD. Okay, of course it's up to you whether you want to tune just the KP, or you want to tune the entire thing, or you want to tune the entire model. Yeah, you can just choose. By the way, this optimization technique is a mathematical optimization. So it doesn't mean it will guarantee you an answer. Okay, but and even if you get the answer, it doesn't guarantee that it is correct. We as the engineers or designers, we need to make sure that it is correct or not. Okay, so I'm going to select the variables that I want to tune. I know I want to tune Ki, I want to tune Kd, and I want to tune Kp. Okay, so, and of course you can select good options and select what algorithms that you want to select. For example, optimization options, you want to select which way of optimizing it, pattern search, syntax search, which algorithm you want to use. Yeah, you can try it out lah. Okay, so after you set all these things, you just I'm going to plot the variables for you to see. I'm going to put this left, right. Okay, so I'm going to add the plot of the variables. So if you see in my MATLAB window, right, currently the value is KD equals to 1, KI equals to 1, KP equals to 1. Okay. So now with optimization technique, I don't need to do any body diagram or whatever. I just click optimize and then let MATLAB do the job. Okay, you can go for your cup of coffee and anything, right? And then you can see how the values change for you, and how MATLAB will find the answer for you. Okay, so let it run. Okay, so now what Simulink design optimization is doing is it is finding an answer to your problem here. Okay. Okay.
So basically, it's plotting the different optimization cycles. Update.
Yep, correct. So it's changing the KP, KI, and KD values to fulfill the white region that you set here just now.
How many iterations did you limit it to?
For actually it will okay.
I mean, ultimately we don't want it to hang lah. So I guess you would
yeah,
to 20 and then let it iterate, get as close as it can to the value lah, based on a specific algorithm, right?
Yep, correct. Yes.
Okay. Okay.
So yeah. So yeah, that's a good question. Actually, you're right. Okay, when I design the variables, right? When I click design just now, right? Let me see this again.
Yeah,
If I edit
looks
it.
like KD
Yeah.
is the one that gets, no, hang on, KP is the one that keeps getting bigger and bigger and bigger. Huh?
Yeah. So yeah. So just now what I did was I put it from minus infinity to infinity. So actually this algorithm actually runs through all the possible values from minus infinity to infinity, and this will make your optimization slower definitely, and
Yeah.
it might give you the wrong answer also. So if as an engineer, if you know your values, for example like Ki, I know that it is yeah, it cannot go below 0, right? And yeah, so you just set it here to help this optimization process easier lah, so that they can do it faster.
But in terms of the iteration, where do you set it? I'm sure there's somewhere to set it.
Yeah, there should be somewhere.
Is it optimization options?
Yeah.
Looks like timeout infinite. No.
Yeah, infinite, yes. But if it can't find an answer, right, it will stop. How it will stop lah.
You will say what? Non-convergence.
Yes, non-convergence. So example, if your yeah, if your cost function stuck at 60, 60, 60, 60, 60, I think around 5 times it will automatically stop, and then it will come out. It will tell you that no convergence is found. And if no convergence is found, one way to solve it is to try another value for the input.
Can you try a different algorithm also?
Different algorithm. Okay.
No, it's fine. I mean, you can do whichever. Yeah. So your one, okay. So you say initially there's a initial guess, is it? Change the
Yes.
initial guess.
What? Yeah. The initial guess just now was 1 1 1 lah.
Okay.
Yeah. So again, because it's optimization, so your initial guess will your final answer will not be the same if you use a different initial value.
Okay.
Okay. So basically, yeah, this is my last demo, and this is the most powerful thing that you can have already, because this totally you don't need to do anything on controls. You just let it tune by itself. Yeah.
Yeah. So look, I'm looking at the iteration, right? Looks like they start with everything 0 or 1, and then slowly increase the KP.
Yeah.
And then slowly increase. Once your KP is high enough, they start increasing the KI lah. And then KD don't do much.
Yeah.
Okay. No. Yeah, I think, I mean, that's also potentially what we would do like on a real.
Okay.
Real
All right. That's great. Okay.
Yeah, we are just KP.
Sorry, you are you
Mr.
are.
Chia, yeah.
Mr. Chia. Okay. All right.
Yeah.
Okay.
Yeah.
So
yeah, I mean, normal control loops, yeah, usually you increase the KP up to a certain level, then you want to minimize the error, you increase the KI lah. And then the error goes to 0, and then you look at the response, maybe you play with D a little bit. Okay. Yeah, very nice, very powerful. Yeah.
Okay, yeah. So yeah, basically that's the end of my presentation. If you all want to actually that is just the control design part. This is a training from our company, applying control design with MATLAB, Simulink, and state flow, and then up to code generation. So this covers a lot of things. Okay, a lot of things. So if you all want to have this training, you can just contact us. You can contact me or Tarma or Hyro, and then yeah, we can help you to arrange lah. Okay, so I'm open for questions now. So yeah, if any of you have any questions, other
There's one question on the code generation. So what it is mainly, I think it's not. Is it RTL or is it C, or I think probably you guys pump it into an FPGA or something.
Yeah, we have we can put it into FPGAs. We can put it into if you are doing hardware in the loop system, generic computer, you can generate generic C code for that, or you can also generate embedded code for more specific processors like ARM processors or ARM SCUs, etc.
Okay.
Yeah. Okay.
Yeah,
Yeah.
I think it's interesting. Yeah.
Okay. All right.
At the moment, yeah. I mean, that's good. I mean, it's a good demo.
Okay. All right. So let us know your feedback.
Okay.
What other topics that you think that are great to have a webinar? Let us know, because it's good to have feedback so we know what will be a proper webinar for the future. Okay.
Okay. Okay.
Okay. So yeah, any other questions from the rest of the people?
No questions here. I
Okay.
think it is. Yeah, I have not seen this in terms of GUI
Control
thing.
design. Oh,
Yeah, in terms of the control loop design. I know we do put stuff in and then we plot the the frequency response, the body plot, and we get
oh,
it.
I see.
But not in terms of, I think maybe we don't
Okay.
have the what do you call, toolbox or whatever. I've never seen it like
I
this.
see. Okay. All right.
So, okay, so basically it's all toolbox, and then you were saying something about fixed point. There's another toolbox
Yeah, that's now toolbox.
for it to be locked to a fixed point.
Yes, correct. Yep. That's now
Okay.
toolbox.
Okay.
Yeah.
Okay. Okay.
Okay. So okay. So if there are no questions, thanks a lot. So that's all from our webinar today. Thanks for attending, everyone.
Okay.
Okay. All right. Okay. Thanks a lot. See you. Bye bye, everyone. Bye bye.